Okay, so I had a kid coughing up his guts in my class today, and I was worried it was COVID. They assured me it wasn't COVID, which kind of reminds me of those people that get bitten in those zombie movies and assure everyone they're okay. All right, question 1. Electron configuration for the chlorine atom. So chlorine has 17 electrons, so you better make sure you account for 17 electrons. And looking at this, it's the third row of the P block, fifth one along. So whatever happens, I'm going to have to end up at 3p5. Alrighty? So it's 1s2, 2s2, 2p6, 3s2, 3p5. Does it add up to 17? 2, 4, 10, 12, 17. Yep. Don't be tempted to put 287. That's the electron arrangement. And that's not, it's not taught in IB anymore. Having said that, what's bigger, the chlorine atom or the chloride ion? So the chloride ion is -1. Chlorine needs 1 electron to take it to 18 electrons to be isoelectronic, same number of electrons as the nearest noble gas. Having said that they don't use electronic arrangements, I'm going to use it to inform my thinking about this one. So the number of protons is the same. After all, it's chlorine. But you should notice that the electrons are different. So for the chloride ion, the Cl-, there's 1 extra electron, and so that's going to cause repulsion with the other electrons in the valence, in the shells, in the orbitals even. So basically, chloride has an extra electron, and that's going to cause repulsion, which will make it bigger. It's 1 point, so it can't be that complicated. Chloride and just more repulsion. You just have to say more repulsion. Okay, not even mention electrons. Why is chlorine smaller than sulfur? 2 points. It's always 2 points. It's pretty much always those atoms as well. So sulfur has 3 shells. 1, 2, 3. And chlorine also has 3 shells, but it's smaller. So what accounts for that? Well, chemistry is basically plus attracts minus. That's so much of chemistry. So in sulfur, you've got 16 protons and 16 electrons. But in chlorine, you've got 17 protons and 17 electrons. Well, what's more attractive? 16 electrons and protons or 17 electrons and protons? Well, 17 electrons and protons are more attractive. So the first point is that chlorine has more electrons and protons and more electrostatic attraction. Plus attracts minus. The second point is, and it's always the same second point, is you have to say they have the same number of shells. If you don't say they've got the same number of shells, or they're in the same period, it doesn't count. And so why is that? Well, let's look at selenium. So selenium is below sulfur, and that's got 4 shells. 1, 2, 3, 4. That's got more protons and more electrons than sulfur, just like chlorine had more protons and electrons than sulfur. And yet selenium is bigger. So why is that? It's got an extra shell. There we go. Is that right? Same number of shells, 1 more proton. That's it. Okay. Moving on, the mass spectrum of chlorine. This was one of the tougher questions on the SL paper, which was very similar to this one actually. So that's the mass spectrometer. The last time I encountered a mass spectrometer, I was at the airport, and they swabbed my fingers and they're looking for NO2 fragments, because most explosives have NO2 on them, the nitro group. I did actually, because I saw on the machine at the airport, it was scanning for that. And I asked the guy, what happens if you test positive? And I don't think they're supposed to answer, but he did. He said they'd ask you what sort of medicine you're on. Because some medicine, for example, heart medicine, contains that nitro group. All right, so there's the mass spectrum. Why are there 2 peaks at 35 and 37? Oh man, it's the isotopes, isn't it? Chlorine 35 and chlorine 37. That was the first calculation your teacher ever did. The IB complained that some people said isomers. No. Isotopes, atoms with the same number of protons, different numbers of neutrons. And for V, what is this peak at 74? Well, you need to know Brinkelhoff. If I ever have a son, maybe I'll call him Brinkelhoff. Mr. Squires from Moscow School told me this. These are all the diatomics. Everything here, Br2, I2, N2, CO2, H2, O2 and F2. So it turns out that chlorine is diatomic. It likes to come in pairs. Well, let's think about it. I could have pairs of the 35 isotope, and that gives me that big peak at 70. To get the peak at the next one along must be the chlorine 35, 37, which is the peak at 72. And the peak at 74 that we're after is chlorine 37, 37. So that's one point, identify the peak. And then they want to know, well, why is it so small? Well, it's so small because chlorine 37 is the lowest abundance isotope. Well, how on earth are you supposed to know that? Well, you do have a mass spectrum here, and you can see that 37 is the smallest peak. It's the lowest abundance isotope. So that was your 2 points. One of the hardest questions on SL. 1B, simple excess and limiting. Calculate the moles of manganese 4 oxide added. Okay, so I've got the mass, which is 2.67. And to work out the moles, I have to use moles is mass over molar mass. So what's the molar mass of manganese 4 oxide? I don't know. The dirty little secret is you probably don't need to use your decimal places, and you'll probably get away with it, especially if you're rushed for time. Right, so manganese, let's have a look. Manganese is 54.94, and oxygen is 16 for the molar mass. (86.94 grams per mole). Okay, 86.94 grams per mole. 86.94. So let's work out the moles. Moles is mass over molar mass. 2.67 divided by 86. 0.03071. All right, I'll stick with 3 sig figs since the mass is in 3 sig figs. Although in reality, you probably want to keep 4 sig figs until you got to the end of the problem. Okay, that's your answer for that. Which is the excess and limiting. I like to use this boxes method. So they're going to have to tell me what's going on in this box, and then I'll work out which one is too much, excess, and which one isn't enough. Hydrochloric acid is a solution, so moles is going to be concentration times volume for a solution. And they better give me those or I can't do it. Concentration is 2.00. And the little trick with volume is you've got to be in decimeters cubed. So I've got 200.0. I'm going to divide by 1,000 to get decimeters cubed. I can do that in my head. 2 times 0.2, it's 0.400. Okay. So 0.400. It seems pretty obvious that hydrochloric acid is an excess. There's loads of it, 0.4 compared to 0.03, but they want you to prove it. So this is how you prove it. What you do is above the reactants, I'm going to put 0.0307 divided by 1 and 0.400 divided by 4. Where did I get those numbers from? Well, there's the 1, there's the 4, and the moles. Whichever is lowest of those fractions is limiting. So I think it's pretty obvious that that's lowest. And so this one is limiting. The IB would accept this as an explanation. Couldn't get any shorter than that. What's the question? Determine the limiting, show your calculation. Yeah. Oh. And that, what are they going to accept? Accept any valid method. Fantastic. Next up, determine the excess amount of moles of the other reactant. So this is how I like to think about it. The HCl is wrong, it's in excess. So I like to think excess, it's wrong, excess, it's wrong. It's the number's just wrong. So I'm gonna cross it out. Let me move it to the side a little. So 0.400, and that's wrong. So what should it be? Well, following the boxes method, the top line is found by using the ratio. 1 is to 0.0307, as 4 is to my answer. So 1 is to 0.0307, as 4 is to my answer. So that's just going to be 4 times that value, isn't it? So I'm going to multiply that by 4, 0.123. So 0.123, but you're not finished. 0.123 is how many moles of hydrochloric acid you used. They want to know how much extra you put in. Okay. So you put in 0.4, you use 0.123. Well, that's the extra stuff, isn't it? So 0. Hold on. 0.400 minus 0.123. That's going to give me 7. Is that 277.277 moles? 0.277 moles. There we go. It's another point. Calculate the volume of chlorine. You could use PV equals nRT, but the little trick, it's only 1 point, so that's a lot of work for PV equals nRT. So what you can do is you can use the data booklet. You can use the data booklet, section 2 of the data booklet. Okay, section 2. We're looking for something to do with gases and STP. There. So 22.7 decimeters cubed of any gas is 1 mole. So we're going to use that idea. So I know that 22.7 decimeters cubed of any gas is 1 mole. Well, how many moles of chlorine do I have? If I had 22.7 decimeters cubed of chlorine, the answer is 1 mole. Okay, so I know that 1 is to 0.0307, as 1 is to 0.0307. So I know how many moles I've got. I've got 0.0307, and this value x will give me the volume of chlorine. Okay. Point 699. 0.699. So my volume of chlorine is going to be 0.699. It comes out in decimeters cubed. Is that what they want? Or they want milliliters? Something tricky like that. No, decimeters cubed. Lovely. Next up, oxidation state of manganese in these. So oxygen, if it's on its own as an element, like every element, has an oxidation state of 0. Oxygen in a compound is always -2, except if it's in this compound, which I think was in the multiple choice, where it's -1. So that gives me manganese must be +4, because it all equals 0. How do I know it equals 0? Because the charge here is 0. If it was -10, it would have to equal -10, but there's no charge. Chlorine's halogen, probably -1. That's unsatisfactory, but it is what it is. And so manganese is going to be +2 there. If you put 4 plus, you lose the point. Has to be +4. I lose a point. Next up, oxidation state is MnO2, an oxidizing or reducing agent. Okay, so do we have the equation? All right, so manganese goes from +4 to +2. It's gone down. That's reduction. That makes sense. So I'm going to put reduction. The number's gone down. And I always think an oxidizing agent is itself reduced. So that must mean that the MnO2 is the oxidizing agent. Oxidizing agent. What's the question? Yeah, there we go. So it's the oxidizing agent because the oxidation state goes down. Is that enough? Yep. Oxidation state goes from 4 to 2, decreases. Lovely. Next up, we're whipping through these. See, chlorine gas. I used to use that to kill people in World War I. I used to send science students, chemistry students specifically out to the front line to kill people with it. And apparently as many people were killed on the German side as on the Allied side. So it was just all round awful. Hypochlorous acid is weak. What's meant by a weak acid? So a weak acid is just partially dissociated, specifically partially dissociated in water. It's got to be the answer, isn't it? Yeah. What's the formula of the conjugate base of hypochlorous acid? So conjugate base. I remember a conjugate acid is made by adding a proton. Well, this is a conjugate base. So that's going to have to be made by removing a proton, an H+. So that's going to give me ClO. No, it isn't. I need that minus there. So that's the conjugate base, ClO minus. It's the concentration of H+. You might need to use the data booklet. It's not particularly helpful here. Topic 8 or 18. Yeah. So you need H+, but H+ is kind of locked in on the wrong side of that equation. So you're going to need the opposite equation to this one. We can do that. So the concentration of H+ is 10 to the negative pH, which is 10 to the negative 3.61. You can't just leave it like that. They won't give you the point. You've got to pop out a number. Now, I remember their answer has 2 decimal places, 2 sig figs. Part of me thinks it should be 3, but anyway. So I think that's pH 2.45, wasn't it? 2.45. pH 2.45. No. What am I talking about? That's the H+, the concentration of H+. Or what was the exponential? Times 10 to the minus 4. Times 10 to the minus 4. Units for concentration are moles per decimeters cubed. They ding you for that? I don't know. No, not this time. Alrighty. Reaction of ethane with chlorine to produce chloroethane. I had kids come out of exams going, we never did this, we never did it. Yes, we did. Initiation, propagation, termination. Oh yeah, that's it. So you can't say initiation, propagation, termination. But you remember that the ultraviolet light hit the chlorine and broke it into homogeneous fission, broke it into 2 free radicals. So it's something to do with free radicals, wasn't it? Free radicals. And you ended up swapping out a chlorine for a hydrogen and then maybe kept doing chlorine for hydrogen swaps. So we don't call it swapping in chemistry, we call it substitution. So it's free radical substitution, they'd accept substitution. What's more reactive, ethane or chloroethane? So one of the first things you learnt in the alkanes is the alkanes are unreactive. And the reason is is because they have strong bonds. Carbon-hydrogen bonds are strong. And the other reason is there's nowhere to really attack an alkane. An alkane is non-polar. Carbon and hydrogen basically have the same electronegativity, the same love for electrons. So that explains why the alkanes are unreactive. Okay, you can set fire to them, but you can set fire to a lot of things, can't you? The reason chloroethane is more reactive is it has a negative and a positive part. So nucleophiles, things that love nuclei, things that love positive things, can attack the carbon, and electrophiles, things that love electrons, could attack the chlorine. So that's one reason. Is it 1 or 2 points? Just 1 point. I bet the other reason is that this bond is weaker. Carbon-hydrogen bond's a strong bond, but this one's weaker. You could check it out on the average bond energies. Okay, bond is weaker or polar bond. You didn't even have to babble on about nucleophiles and whatever. You just had to say it was polar. Next up, chloroethane and aqueous sodium hydroxide, curly arrows, la-di-da. So that's SN1, SN2. Now, I've not thought which one it is yet, but it's 3 points, so I bet it's the more complicated one. Anyway. So the way I remember it, a kid called Tent in Thailand explained this to me, was 1, 2, 3, bang. He's now working on the Mars, that Mars rover that just landed. So SN1 is 2 steps, and it's for tertiary haloalkanes. So we've got chloroethane, that's a primary haloalkane. So that means it's going to be SN2. So this is going to be SN2. How do you know it's a primary haloalkane? Well, here we go. Find the halogen. Find the carbon attached to the halogen. How many carbons are directly attached to that? Well, just this one. Well, it's primary. So SN2, that's going to be 1 step. So I was wrong with my initial assumption. And it's for primary haloalkanes. Now, sometimes they want you to show the intermediary step, but from the question, it doesn't seem that you need to do that. But don't forget your curly arrows. Curly arrows show the movement of electrons. This is the movement of 1 electron. This is the movement of 2 electrons. This is the movement of 5 electrons. Kind of fun. All right then. So chloroethane. All right then. So it's 1 step. Chlorine loves electrons more than carbon. It has a higher electronegativity. So those electrons are going to go to chlorine. And then the electrons from the OH. Now normally they don't care if you take the arrow from the minus or from a lone pair on the oxygen. I'm just going to check the answers to see if they're fussy about that. Curly arrow from the lone pair or the negative charge on the oxygen. Okay, yeah. And so let's take it from here. And those electrons are now going to be attracted towards that positive carbon. And so what you're going to get at the end is you're going to get the alcohol, ethanol. What a tricky way to make alcohol, eh? You're going to get ethanol. Well, a lot of people just leave it at that, but don't forget you've now got the chloride ion as well. You've got that. Okay. Oh, did they want the intermediate? Come on. Explain the mechanism. Curly arrow going from here to there and there to there, 1 point. Curly arrow showing that leaving. Representation of the transition state? You dirty devils. What's this representation of the transition state? Come on. That's not fair. That's not in the question. All right then. Dirty devils. So let's move this over here. So you've got to show what's happening when the OH minus is popping on and the chloride's popping off. Now that involves 3D geometry. Do they want the 3D geometry? So I had to show dotty bonds to show that the OH minus is coming in and the Cl is coming off. You still wouldn't get a point for that though, because of course you need square brackets, and you still wouldn't get a point for it because overall this weird pentavalent carbon is negative. I'd be fail on that. Next up, draw ethoxyethane. A little visited part of the syllabus. 50% of the SL got this right. So if it's got an oxy, then it has a carbon, oxygen, carbon, and you can see there seems to be an eth at both ends of the word. So there's an eth at both ends of the molecule. Ethoxyethane. Almost certainly, I think this is a sedative, a bit like this video. Alrighty. Draw the structural formula. Lovely. Ooh, H1NMR with splitting. I do like H1NMR. I don't know why. Okay, so first of all, let's work out, well, H1NMR, it tells you it only works if there's H atoms. So the H1NMR for tetrafluoromethane, there's nothing. Carbon dioxide, there's nothing. It's got to be hydrogens. So the number of peaks tells you the different types of hydrogen environments. The area under the peaks tells you the ratio of the hydrogens in those hydrogen environments. And the location of the peaks tells you about that hydrogen environment. Is it a methyl? Is it in an alcohol or whatever? And then the fourth thing, the splitting, tells you how many hydrogens are on the adjacent carbon plus one. That's the splitting number. I wanted to be a drummer. Okay, so how many hydrogen environments? I see 2 hydrogen environments. This, that, and that. So that's a hydrogen environment there with 6 hydrogens. And that leaves me with this, and this, and this, and this. You have to look at my video on hydrogen environments if you can't follow what's going on. So there should be 2 peaks. Okay, 2 peaks first of all. One's going to have an area of 6 and one's going to have an area of 4 because there's 6 to 4. 2 peaks. Now where am I going to put those 2 peaks? Let me take a look at the data booklet. Infrared. So where am I going to put those peaks? Well, it looks like I had a CH3, so 0.9 to 1. And then it's tempting to think, oh, there's CH2. No, that oxygen has to be accounted for. So it's going to be down here, isn't it? It's going to be down here on this one. So that's a 3.3 to 3.7. Alrighty. So it's 0 at about 1 here. And then over here, what was it, 3.3 to 3.7? So let's say that's at 3.4 or something. So this was going to have an area of 6. And this was going to have an area of 4. But that's not enough for the points. Deduce the number of signals. So the number of signals is 2 signals. The chemical shift. So the chemical shift was 0.9 to 1 parts per million. And the other chemical shift was 3.3 to 3.7 parts per million. And the splitting. Okay, so splitting. Let's pick this hydrogen here, because there's 5 others like that as well, isn't there? In that hydrogen environment, count the number of hydrogens on the adjacent carbon and add 1. Okay, the adjacent carbon isn't that one. The adjacent carbon is this one here. There's 2 hydrogens plus 1, it's 3. So that big 6 peak should be split into 3. So it should be ding, 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 like Lord of the Rings, with an area of 6. Let's take a look at the second hydrogen environment, which was this one here. How many hydrogens on the adjacent carbon? Well, that isn't the adjacent carbon, it's 1 over. So there's 3 hydrogens on this one. Plus 1 is 4. So that's going to be split into 4. So it's kind of going to be 1, 2, 3, 4 with an area of 4. So this is called a triplet. And the 4, I think, is called a quartet. That's a lot of work for 3 points. Is any of that right? 2 signals. Oh, they wanted to know which one was the triplet, and which one was the quartet. So I think it'll be clear from my diagram, but just to let you know, that was the triplet, and that was the quartet. All right. Next up, calculate the percentage by mass of chlorine in that. This was the easiest question on the SL one. Didn't have much to say about the HL. Did I have any comments here? Okay, so I need to work out the molar mass. It's 12.00 plus a couple of fluorines, and a couple of chlorines. That's the molar mass of the compound. And the chlorines, well, there's 2 of those, isn't there? So I'm going to put that at the top. And it wants percent, so I'm going to multiply that by 100. So that's going to give me 54.64%. That's 54.64%. Okay, I'm done. Let's do some more tomorrow. Oh, excuse the strange angle up my nose here. So next question, international cooperation for CFCs. Well, that was the Montreal Protocol. That was an international agreement that actually worked. It's held up as one of the most effective international agreements. The governments chose to ban CFCs. You could get that as a point, Montreal Protocol, or you could also mention that they actually have alternate technologies. They actually took the CFCs and they made HCFCs. HCFCs, that's a lot less of an ozone depleter. Unfortunately, it's a greenhouse gas, so just a different disaster. All right then, and the next one, few could do, but I think you could work it out from first principles. Chlorine radical reacts with ozone. Well, let's put a chlorine radical in and some ozone. There's not much that could happen. I mean, they could all add together, couldn't they? But probably I'm going to make some oxygen and a ClO dot. Now, the IB puts its dots in different places to where I learnt at university. But if you don't put the dots in the right place, you will lose the point. That dot is a lone electron, an unpaired electron. And then what else could you do? Well, let's take the most reactive product there, ClO dot, and then react it with something else. Well, I could react it with more ozone, or you know what? I could even react it with some O dot. Where the heck did that O dot come from? Well, the O dot comes from the equation that you don't need to write down here. UV breaks into O2 and O dot. That's how it protects you from the sun's rays. The UV breaks the ozone instead of breaking you. All right then, so what are we going to get here and there? So you've got a choice of either of these two for the second point. So it's going to be Cl dot plus O4. That would be insane, O4. No such thing as O4. So it's 2O2. And if you don't like that one, I think I've got an oxygen here and a Cl dot. Although, to my mind, those dots feel like weird. But that's how the IB likes it. They want the dots there. All right, that's question 1 done.